Rec- Recording, Eduardo.
Great.
Okay.
Many
Okay.
thanks.
Well,
Okay, so
hello, and afternoon. Good afternoon, everyone. I am Eduardo Serpa. I am the chair for today's second seminar. I'm very pleased to introduce Giuseppe Maria Coclite, from Polytechnic di Bari in Italy. Giuseppe, well, he got his PhD in mathematics in 2003 from CISA Institute in Trieste. He was a postdoc in the Center for Mathematics for Application in Oslo, Norway. Since 2005 to 2016, he got different positions at the University of Bari, and since 2016, he is full professor at Polytechnic di Bari in Italy. Okay, I would like to mention that Giuseppe, well, is part of different editorial board of relevant journal in mathematics. He has written many fundamental works in PDEs, nonlinear analysis, control, and conservation laws. For today, as you can see in your screen, the title of his talk is Vanishing Viscosity versus Rosenau Approximation for Scalar Conservation Laws, the Fractional Case. So please, Giuseppe, you can start.
Eduardo, many thanks for the very nice introduction, and many thanks for to the organizers of this seminars for the invitation. It's really a pleasure. Before then I start with the mathematics, let me quote that the co-authors of this paper are Nathalie Alibaud, Maxime Dallery, and Carlotta Donadello. All of them are in Besançon, in France. And the results were published on JD in 2025. So let me start spending a few minutes to introduce you to the key of the problem. So the starting point are the multi-D scalar conservation laws. And multi-D scalar conservation law is an equation like this: omega t plus divergence of f of omega equals 0. Here t is positive and x is in Rd. And the initial condition is omega naught x, and this is for x in Rn. Now, before the assumption, let us pick some notation. First of all, you see here x will be in Rd, and d will be bigger or equal than 1. Second thing that is important, when I write omega, I mean a function, I usually write time and space. And this is a scalar quantity. So this is an equation in Rd, and we are working on the Cauchy problem. So in this talk, we don't consider any kind of boundary. Now, the assumptions. The assumptions are not complicated. F is a W1 infinity loc vector, function, vector valued. And the initial condition is in L1 Rd, intersection L infinity Rd, intersection BV in Rd. I know that in some communities, like the calculus operation community, when you write BV, you already mean that the solution is in L1. The people in conservation law usually, when they write BV, they simply mean that the derivative of omega naught is a finite measure. Now, which is the main feature of these kind of equations? Main feature. The main feature is the spontaneous creation of singularities. And spontaneous means that you have the creation of singularities in places where, I mean, at time zero, you don't have any kind of singularity. The prototypical example that you see on every book on conservation laws, and on this example, you have also the explicit computation, is this 1D system, omega t plus omega square over 2x equals 0, with omega 0x equal 1 over 1 plus x squared. Now, if just formally you here compute use the chain rule, you know that you have this identity. So this means that if you use the characteristics, you see the speed depends on the eight of the function. So this point is going much faster than this point, much faster than this point. So at the end of the day, you have the creation of a singularity. And you see, you have the creation of a singularity, and I mean, here I'm just making a picture, and so making everything qualitative. But I mean, if you pick a book on conservation laws, you have all the computation on this. So you see, we have the creation of singularity, and we started with a function that is analytic. So you see, I mean, you can have the creation of these singularities whenever, independently on the smoothness of your initial conditions. So, you know, I mean, you people are people in PDs, and you know that if you have to deal with the solutions of a PD that are not classical, not regular, you have to work with the distributional solutions. And this is something that you know, but immediately, as soon as you start with that, you have a big problem. Distributional solutions are not unique. And this is a big problem because you see, conservation laws try to model the dynamics, for example, of vehicular traffic or of a gas or a fluid. I mean, so when you work with these kind of PDs, you want a concept of solution that is giving you the uniqueness. This problem of the lack of uniqueness was solved by Khrushchev. Let me write. I hope that the spelling is correct. I'm always wrong with the spelling, but I hope that is correct. With Khrushchev in a celebrated paper in 1917, in which, in a way, he used the second principle of thermodynamics. So Khrushchev suggested to use the concept of entropy solution. The solution. An entropy solution is a solution that is doing this. For every atom that is in C2 of R, and for every Q that is in C2 of R with values in Rd, such that you have that eta second is convex, so eta second is positive, and Q prime is equal F prime eta prime, you must have this inequality, eta omega t plus divergence of Q omega less or equal than 0. And this is a definition, I mean, it's a very deep definition. And I want just give me 1 minute because I want just to give you a small taste of the complexity and the deep thing that are written here. So let me fix a function eta that is C2. We fix the function q such that q prime is equal f prime eta prime, and the computation that I want to do with you is this one, eta prime u multiplied by the equation. The equation is, this is omega. Divergence of f of omega. Oh, this is 0, because you see this is 0. This is a formal computation, but I think that is useful. You have eta prime omega t plus eta prime omega f prime omega times gradient of omega. Now, you apply the chain rule, you obtain that this is eta omega t plus this is q prime, so you have divergence of q of omega. So, the fact that you have this expression, I think that now is clear. What is important to notice is that in the definition of entropy solution, first of all, we don't have equal 0, but we have lesser equal than 0. Second thing that is for me more important is this one. Look at these simple 3 lines that are written here. In these 3 lines, I applied the chain rule here, here, and here. So you see in 3 lines, 3 times. Now you know that if you have a discontinuous function, you cannot apply the chain rule. So you see, entropy solutions are, in a way, distributional solution with this special property that you can apply, in a way, the chain rule. Of course, you lose something. You get less or equal than 0, not equal 0. But anyway, you can apply the chain rule. One final comment on entropy solution is this one. If you look at the paper of Khrushchev, he was not writing the definition of entropy solution in the same way in which I've written it. He was writing something like this. For every C in R, absolute value of omega minus C t plus divergence of sine of omega minus C, f of omega minus f of C, less or equal than 0. So in a way, it was using this eta, omega minus C, and this q. Q of omega equals sine omega minus C, f of omega minus f of C. Now, why, for me, these entropies are interesting? Okay, they have one good thing and one bad thing. The bad thing is clear. This is not a C2 function. So you see, that's a bit annoying. That is a bit annoying. But it's convex, but it's not C2. What is good is that the number of entropies that you are considering in this definition is much less than the number of entropies that I was using in the previous definition. Before I was considering every C2 function, so that is an infinite dimension manifold in the space of function. Here I'm considering a manifold of dimension 1. So you see, again, you have these things that are absolutely not obvious. Now, entropy solution have this property. If you have 2 solutions, then you have this inequality. Omega t dot minus omega bar t dot inner 1 RT is less or equal than the distance at time 0. Oops, 0. So you see, the solutions are, the entropy solution is unique. If the initial condition is the same, you have 0. And you have also the continuity, the Lifshitz continuity with respect to the initial condition. Now, so this is the concept of solution that we are going to use, but now I want to focus on what is missing in what is written here, because when you do well-posedness, you have existence, uniqueness, and stability. Here we have uniqueness and stability. What about existence? And for the existence of entropy solution, you have to be careful. There are a lot of ways. For example, you can use the numerical approximation to discretization. But the kind of approximation that I want to discuss with you today are the singular limits. So, singular limits. So, in a way, I want to perturb my conservation law and pass the limit. Now, you have to be careful because not all the perturbation work. For example, if you use this perturbation, call this omega epsilon, div f omega epsilon equal epsilon. Let me put even in 1D. Omega epsilon x. This is named vanishing dispersion. Then Lux and Livermore in 1989 proved with an example that omega epsilon is not converging to omega. When I write omega, I mean the entropy solution of the problem. So you have to be very careful when you do these kind of singular limits. The first singular limit that has been considered in the, at least is the most celebrated singular limit, is the vanishing viscosity. The vanishing viscosity is this one. U epsilon t plus div f u epsilon equal epsilon Laplacian u epsilon. And of course, you put at time 0 the same initial condition. All these problems are with t bigger than 0 and x in Rd. Now, Khrushchev proved in 1970, that you have two things. First of all, that u epsilon is converging to omega in LP log of R plus time Rd. And this is true for every p with p between 1 and infinity. And you have also that the convergence is almost everywhere in R plus time Rd. Then there are two papers, one by Kuznetsov, 1976, and another paper by Katsoulakis and Tsavaras in 1997, in which they improved the result of Khrushchev, proving this. If you do u epsilon minus omega in C of 0t with values in L1 Rd, this is less or equal than C square root of epsilon. So they proved this error estimate. And notice that you have the convergence not of a subsequence, but of all the family. Of course, when epsilon is tending to 0. This is the first approximation that we are considering today, and then we are also considering this other approximation. This is very popular between the engineers, not very popular within mathematicians. So this is the Rosenau approximation. And the Rosenau approximation was introduced in 1982. So Rosenau proposed to use this approximation, div f V epsilon equal minus epsilon f minus 1 dot square 1 plus epsilon dot square f v epsilon. Initial condition is the same. And why this approximation is interesting? Okay, this is the Fourier transform, of course. And this approximation is interesting because, you see, if you write the Laplacian of a function in Fourier, with the Fourier transforms, you have this identity, dot square f phi. And you see that when psi is very small, then you have that the Laplacian of phi is more or less the same of the Fourier, the Rosenau operator. So this is an approximation phi. It is a kind of Laplacian that is acting only on the psi that are very small. Well, again, in the paper of Katsouladis and Tsavaras, the one that I quoted before, they proved that V epsilon converges to omega in LP lock, R plus time RD. Again, 1 less or equal than P less than infinity, and almost everywhere in R plus time RD. But in particular, they proved another error estimate. The error estimate that they proved is this one. V epsilon minus omega, again, the space is always the same, C0 T with values in L1 are dim, is less or equal than C square root of epsilon. So, you see, here we have omega, that is the solution of the conservation law. We have U epsilon, that is the solution of vanishing viscosity. V epsilon, that is the solution of the Rosenau approximation, and we know that the distance between V epsilon and omega, and okay, I don't put specify the space, it's always the same, and the distance between U epsilon and omega have the same order. They go like C square root of epsilon. So the question that I want to answer today is, what happened when I compute this is U epsilon. Is this much less than U epsilon minus omega plus V epsilon minus omega? This is the question that I'm asking. So, in a way, if you try to imagine that omega, U epsilon, V epsilon are points of the plane, you have here omega. So the question is, are we in this kind of configuration that you have U epsilon here and V epsilon here, or we are in this other configuration that here you have omega, here you have V epsilon, and here you have V epsilon, U epsilon. So you see here, if you compute this distance, is of the same order of this distance. Here you see that these two distances are much bigger than this one. So which is the case? Well, the case is this one. But unfortunately, we are able to prove it only in the fractional case. So let me try now to put the to state precisely what we do, because now we have to pass to the okay, I see that it's already 2017. I have to go a bit faster. So fractional case. Okay, so just to be clear about the notation. This is the conservation law. This is the fractional vanishing viscosity. This is the fractional Rosenau. And I mean, Laplacian alpha over 2 of a function is nothing more than this one. And the Rosenau operator with exponent alpha is nothing more than this one, f minus 1 alpha over 1 plus epsilon alpha f of phi. And which are now we have well, okay, immediate comment that I want to do. First of all, okay, epsilon is bigger than 0 and is going to 0. Alpha is fixed and is a number between 0 and 2. Okay? Now, observe that here you have at least 4 cases that you have to consider. The first case, let me write regimes. The first regime is the regime when you have alpha equal to. This is the regime that is the non-fractional case, because when alpha is equal to, this is the Laplacian and this is the classical Rosenau operator. The second regime is when alpha is between 1 and 2. This is named the subcritical. And why is named subcritical? Because you see, even if this is not anymore a Laplacian and this is not anymore the Rosenau operator, anyway, the order of these two operators is bigger than the order of the convection. So in a way, these are the dominating operators, and you have the regularization effects. The case that is, at least for me, was in a way discovered is the case alpha equal 1, that is the critical case. Again, the case when alpha equal 1 now is a strange, at least for me it was strange, because you see, when alpha is equal 1, in a way you have first order, first order, first order, and first order, but still, these operators have a kind of regularizing effect on the convection term. And the final case is the case when alpha is smaller than 1 and bigger than 0, in which we have that is supercritical. And this is the case in which you have that these operators are the operators of lower order, and this one is the dominating operator. Well, on this problem, you have these results that I have to quote before telling you what we did. The results is that you have an estimate on u epsilon minus omega, always in the same space, and v epsilon minus omega. That is, the order of this distance is this one, epsilon 1 over alpha, if alpha is between 2 and 1, epsilon log natural log 1 over epsilon if alpha is equal 1, and epsilon if alpha is between 0 and 1. These were things were proved by Alibo and and collaborators in 2-3 papers. Now, which are our results? First of all, we proved that, let me call this star are optimal. Second, we give a precise estimate on u epsilon minus v epsilon. Now, I think that is a bit useless now that I write you the precise expression of this distance. What is important for me is to explain you why these results are important, why they have to be quoted in this order. First of all, why is important? What does it mean that these estimates are optimal? This means that we were able to show some examples in which you don't have the inequality, but you have the equality. This is important because if you look again at the picture that I made before, if you have this picture, now you know that this distance and this distance, you know precisely that they are not simply less or equal, for example, than epsilon. I think that probably I forgot. No, epsilon. You know now that they're exactly of the order of epsilon. Since I want to compare these two length with this length, it's important to know that this is not simply less or equal than epsilon, but is of the same order of epsilon. So now that we know that these two lengths are not simply less or equal than epsilon, okay, here there is a constant, but they are exactly of the same order of epsilon. When you do the precise estimate on this distance, now you can say that this is true, that u epsilon minus v epsilon is much less than u epsilon minus omega plus v epsilon minus omega. You can say this because, first of all, you have this estimate, and second, you know precisely which are these lengths. If you don't prove with some examples that these estimates are optimal, then I mean you cannot say that this is true, because maybe it's simply that these estimates are not good enough. I mean, they are good because we proved that they are optimal. Let me just tell you which is the idea of the proof. And in order to prove this estimate, well, first of all, we prove this only when alpha is strictly less than 2. And our arguments don't work with alpha equal 2. All the estimates blow up when alpha is going to 2. So, I mean, alpha equal 2 is missing. But we have two different arguments when alpha is between 1 and 2, and another argument when alpha is between 0 and 1. Okay, about this one, I simply tell you that here you have to use the Kuznetsov type argument, the spelling Kuznetsov argument is an argument that, if you know the error estimates for conservation laws, is there. So to be frank, this is the part that was less surprising, at least for me. What I found very interesting is the approach that we used here, because the approach that we use here is to see the vanishing viscosity with the fractional vanishing viscosity and fractional Rosenau, like Levy, conservation laws with Levy operators on the right hand side. So the trick that we used is that we picked, for example, the vanishing viscosity, that is this one, and we recognized, sorry, this u. So this epsilon Laplacian alpha over 2 u epsilon. And we wrote this in this form as a L mu of u epsilon. Now, what are these, what I mean with L mu? L mu is what I call a Levy operator, and Levy operator is an operator that has this kind of structure. L mu phi of x is equal to the integral over Rd of phi x plus z minus phi x minus gradient of phi x z key z less or equal than 1 in z d mu z. And you can do the same game with the Rosenau approximation. So you have v epsilon t plus divergence of f v epsilon equal epsilon, what I wrote r alpha epsilon v epsilon, and you write this as epsilon L nu v epsilon. And what is important here is that you can play this game only when alpha is between 1 and 2. Playing this game and using the fact that on the conservation laws with Levy operators on the right-hand side, you have an extremely precise theory. In particular, you have the continuity with respect to the measure, so very precise estimates that on the dependence of the equation on the measure. I mean, this was the idea. Eduardo, I think that my time is over, so I think that because now, I mean, the things get simply more technical. I mean, these are the ideas, so I think that I prefer to stop here.
Thank you. Thank you, Giuseppe, for the nice talk. I think that the handwriting can be read very well, so don't worry. It was very, very nice. Okay,
Thanks.
we can
Thanks.
follow your rhythm, so very good. Thank you.
Thanks.
We can open the mic for questions, please. If you have one, just you can ask it or put it on the chat if you are not allowed to speak loud. Okay, so don't be shy. I have a couple of questions, Giuseppe.
Sure.
For if you are interested in approximating this this solution, and for instance, for numerical reason, maybe one of the two paths is better, or maybe for other issues, it's clearly one option is better than another one. Can you comment on this, maybe?
Huh. Mhm. To be frank, well, I mean, one thing that you can do is to try to play the same game with two other approximations that are more, I mean, numerical approximation. The problem, if you want to put some numerics in what I described you, is that when you use numerical schemes, you know that you are adding some additional viscosity. So in a way, I mean, all the things that are here is that you try to be as precise as possible with the perturbation. Now, if you add some additional viscosity, in a way, you are ruining all the estimates. That's my point. But to be frank, I'm not sure that I can answer to your question, Eduardo. I'm sorry.
Okay, okay, don't know, but and the other question is if what happened when in the case that f is linear? So in the linear case,
Well, I mean, in the linear case, you have the examples. And in particular, we did one example with f equal completely 0. And
Okay.
there we did all the computations, and we showed that these estimates that are written here, you see, are precise. So when I wrote these are optimal, we did the our example. One is in the linear case, and the other one is for the Burgers equation. And there
Okay.
we really computed everything. I mean, every single detail, and you can prove exactly that this is true. So in the sense that this distance is really order epsilon. This is what I mean. It's
Okay.
not less
Okay.
than epsilon. And also for the other cases.
Nice. Nice.
So
Uh,
I don't think that if you have a linear term is very different from the stationary case. Because you know that when you have something linear, you have simply that the characteristics are banded instead of having right, I mean that they are standing like this. So my impression is that it should, I mean, our example should work even in a more general, in a simply, in a general linear case.
Good.
I,
In the case for the equation, what you need, for instance, this viscosity solution concept, do you know some control results for them, or an example, some
no,
paper? No.
no, to be frank, no.
Okay. Okay. I think that there is maybe a delay with what we are looking at on the screen, but it's
No,
not.
no, it's simply that they put page 12. You see?
Okay. Okay. Okay.
I simply that I put the not the last page.
Perfect. Well, I don't know if there is a question in the audience. Okay. If not, I think that we can thank Giuseppe again. Thank you very much for your
Thanks.
nice talk and for being able to participate in this kind of traditional now seminar here organized from the team led by Juan Limaco. So thank you
Thanks for the
Thank you
invitation.
very much, Giuseppe.
It was really nice.